Great. Hello and welcome to Powering the Future. This is a webinar and it's first in a series of many webinars to follow. And the topic will be on hybrid energy storage. And this webinar, this current edition, is presented to you by the European projects HEVEN, SMHYLES, and HIHELIOS. Now, let me introduce myself. My name is Daniel Kiesling. And when I'm not supporting the project SMHYLES in communication dissemination activities, my day-to-day business is supporting consortia, so you, with the application of Horizon Europe funding. We are a publicly funded agency from the government of Bavaria. Let me head over to the agenda. Now we have a packed agenda with a lot of interesting topics, and let's say we will not discuss everything, but like I just said, we will also have additional webinars. So we will start with short project presentations of the three projects, HEVEN, SMHYLES, and HIHELIOS, 10 minutes each. Then we will have a panel discussion on, let's say, previously selected questions, where we keep discussion about hybrid energy storage, the barriers, the applications, and so on. This will be followed by a Q&A session where you have the opportunity to ask questions or where there is room to discuss even more. And we will end with closing remarks. Now, very briefly, the webinar guidelines. Please keep your microphones muted, so we don't want any background noise. If you have questions, please use the, so I see now we have a chat and a Q&A button, so you should use the chat button to ask your questions and we will monitor those. And yes, we will then try to answer all the questions, hopefully in the end. The webinar is being recorded. So if everything turns out fine with the recording, then we will be able to share this. The same is true for the presentations. Now, without further ado, I want to head over to our first project, that is HEVEN. And it will be presented by Christopher Joseph Haruna. He's the coordinator of HEVEN. And he is Technical Project Manager at Brussels Research and Innovation Center for Green Technologies, short BRIN. He has a Master of Science in Transportation Science from the Hasselt University. And according to his LinkedIn, he is a green mobility and renewable energy Jedi. So even though it's not May the 4th today, it's April 4th, but I'm very much looking forward to your presentation, Christopher, please.
Thank you very much, Daniel, for such a rousing introduction. Good morning, everyone, and I'll be welcoming you to this presentation on HEVEN. And when I'm not managing this project, I'm probably somewhere playing chess. So this is the introduction to HEVEN, and HEVEN is an acronym for High Performance Hybrid Energy Storage System for Multi-Service Provisioning, and it's a European project. Can you move to the next stage, please? Before I start anything about this project, I'd like to throw us back to Energy Storage 101. I know most of us here are aware of this topic, but what is energy storage? And energy storage can be defined as capturing and holding energy in reserve for later use. And in this case, this brings us to hybrid energy storage systems. What are hybrid energy storage systems? These are storage systems that are comprised of two technologies, whereas there is a combination of one that stores energy for extended usage, and another that stores power for instantaneous release. A current multiplied by voltage released instantaneously. So a HESS system is a combination of these two batteries that comprise of these two technologies. That being said, we move forward to introduce HAVEN properly. So HAVEN is basically a hybrid energy storage system that utilizes next-gen storage technologies and optimized power converters and advanced EMS and state-of-the-art tools for measuring the scalability and cost effectiveness of the project. And in this case, we have a digital twin incorporated into the project. Next slide, please. So the operational objectives of HAVEN basically is to develop and demonstrate an improved HESS architecture utilizing heterogeneous storage and battery system arrangements to optimize the state-of-the-art power conversion devices, to develop and validate advanced control systems, to develop a modular design platform and digital twin for the HESS diagnosis, and to assess the life cycle of the HESS system, its components, and establish an adequate critical raw material recovery plans. I think, and lastly, to maximize a wider uptake of HAVEN's results during and after the project's duration. So let's talk about the methodology of HAVEN. As I had earlier stated, that HAVEN is a combination of a high energy battery and a high power battery. In this case, what brings out the best from this combination of batteries? HAVEN utilizes a hierarchical energy management system. The EMS basically is broken into 3 levels: the lower level, the medium level, and the high level. And these all utilize predictive and they leverage predictive and optimization algorithms for efficient energy management of both batteries. HAVEN also incorporates a digital twin, and this digital twin gives a real-time state of the battery to to ensure that during operation, the battery state of health is kept at its optimal at an optimal state. And of course, the DC-DC converters that HAVEN utilizes have cognitive functionalities. Now, we move forward to look at the use cases that will be demonstrating the HESS. In this case, we have the use case that enables ultra-fast EV charging, and this is proudly hosted by our partners, Imekar in Turkey. In this case, the hybrid energy storage system will demonstrate how it can manage services, support services such as peak shaving, load leveling, and load balancing, basically. The next use case of HAVEN is hosted by our partners, Solitech in Lithuania, where a multi-purpose building will be demonstrating the services of the HESS. In this case, as we can see in this diagram, the building incorporates various load profiles such as heat pumps and charging stations, and of course, we'll be seeing services such as peak shaving and load leveling, mostly for the HESS solution. The next use case, which is one of the most interesting, It's hosted by our partners, DTU in Denmark. The HESS will basically be testing, will be demonstrating services such as frequency change in this hybrid power plant. And the last use case would be a virtual use case that will be validating the digital twin of Haven. Moving on to the next slide. Haven follows a 48-month work plan, and currently we are at month 16, and I'm excited to tell you that we are 27% complete. We have completed a number of work packages, and the plan revolves around basically the technology development and system integration, the system demonstration, the socio-environmental assessment, and the outreach strategy. To the next slide, please. So a number of work packages explain or portray the methodology of Haven that I had earlier explained, and Haven is broken down into work packages. So work package 1 is about the specifications and requirements of the HESS system. 2, models tools, which of course has the EMS and the digital twin. Work package 3 is the cognitive power electronics. 4, the development of the battery itself. Work package 5 is the assembly of the HESS system. Work package 6, demonstration 7, is about the socioeconomic assessment, and work package 8 and 9, which is the DCs and the project management. Next slide, please. So the outcomes of Haven is basically to demonstrate hybrid energy storage technologies with improved technical performance, to enable improved localized cost of storage, putting the cost of storage to fall at 0.05 euro per kilowatt hour by 2030, to increase digitalization from design to operation, to create synergies between producers and strengthen the EU battery ecosystem, the establishment of multi-service approach to energy storage to reduce costs, and also to promote and increase reliability and resilience of the electricity system. So based on the objectives of Haven, we are hoping that Haven paves the pathway for more efficient HESS solutions, reduce costs, and advanced control systems that can optimize and bring out the best out of hybrid energy storage systems at large. The Haven Consortium is made up of the following partners, and they run along different parts of the world, from Africa to Europe and Eurasia. And this is how I decide to use my 10 minutes for this presentation. Thank you so much.
Perfect, on time. And I think also a lot of connection points to the discussions later. I just checked the chat window, so I don't see any questions. Hopefully this is not only the case because I'm not a moderator, but yeah, but I think there are no questions at the moment. If you have questions, raise them in the chat, please. So I will head over to Eduardo Ginomacchi from the Fondazione Bruno Kessler. And he's head of the Battery and Electrification Technologies, BET, unit in the Center of Sustainable Energy. He has an engineering background, and since 2018, he has been in charge of battery R&D activities at Fondazione Bruno Kessler. He performs different coordinating activities, from material development to battery system prototyping and testing. He is responsible at FBK for the IPCEI or IPCEI European Battery Innovation activities, and he is also the representative for the BUT for EU partnership. So a lot of networking opportunities there. And he's actively contributing to several working groups. So without further ado, Eduardo, please, the floor is yours to present the project SMHYLES.
Thank you very much, Daniel, for your kind introduction, and good morning, everybody. So today I will be presenting the project SMHYLES that I am coordinating as FBK, let's say. So going to the next slide, what's SMHYLE about? SMHYLE stands for Sustainable, Safe and Sustainable Modular Hybrid System for Long Duration Energy Storage and Grid Services. The project started at the beginning of 2024 and will last 48 months. The total cost is around 7.6 million euro, with a total funding from EU close to 6 million. And in this project, we are targeting TRL 7. In brief, in SMHYLES, we plan to design, construct, and demonstrate two hybrid energy storage systems based on low CRM storage technologies. The first one is an aqueous hybrid energy storage system based on a combination of a vanadium radius flow battery and a nickel carbon aqueous supercapacitor, while the second system is a salt-based hybrid energy storage based on sodium chloride molten salt battery and an nickel carbon aqueous supercapacitor. However, in SMHYLES, we are also targeting the study and the demonstration of hybrid energy storage retrofitting and storage expansion with another demonstrator. And of course, there are a lot of activities that are related to the development of digital tools that will support the HESS design and management. Of course, at the key of our project are also smart energy management system and the development of advanced grid forming capable power conversion system. So next slide, please. So our consortium is made up of 14 partners from 5 EU countries and 2 partners from Switzerland and Tunisia. We have energy storage technology manufacturer, storage system operator that will be in charge also of the demonstration, 1 PCS manufacturer, 2 engineering companies, 4 research and technology organization, 2 university, and 1 non-profit entity that is supporting the dissemination of the project. So SMHYLES objectives are connected to different, let's say, key areas. Regarding sustainability, in SMHYLES we target a carbon footprint reduction of at least 40% compared to standard state-of-the-art battery energy storage system. We are also targeting improved energy and power density compared to single energy storage. We also want to develop tool and model that allow us to have a better prediction of the storage behavior, also supported by the development of digital model and digital twin. And of course, we are also targeting a better reliability and techno-economic feature of the system with a longer system lifetime, thanks to the hybridization. And then also putting, let's say, the cost per kilowatt hour per cycle to go below 0.04 euro per kilowatt hour per cycle. Next slide, please. So the project is focusing on 3 pillars, 3 innovation pillars. One on digital tool, the second on the energy storage technologies, and the third on the integration. On the first pillar, we are focusing on the development of tools for the optimal design and for the optimal management. Of course, some of those will be also data-driven. And we are also building digital twin for the management. Regarding the energy storage technologies, we are working on safe and sustainable aqueous supercapacitor module that are suitable for stationary application. We are also working on flexible and modular reduced flow batteries. And in the project, we are also focusing on advanced BMS for salt batteries. Of course, it's important to integrate all of these innovation into the hybrid. So we are working on advanced EMS with different feature based on each demonstration that I will present you later, and on working also on grid forming capable power conversion system that allow the optimal integration between the two storage into the ES and between the ES and the grid. Next slide, please. Okay, here you can see the work plan of SMHYLES. Of course, we are coordinating the project in WP1, and we have Bayfor in charge of WP6 on business planning, exploitation, and dissemination, while the 4 technical WP are, let's say, are focused on the different phase of the project in the end. The first phase is related to the design of the system. This is also completed, that we will see later, and it is done in between WP2 and WP3, and it's concerned the design of the system, the development of digital tool for the design, but also for the management. Then we are already started with the phase related to the development of the system, where we are introducing the innovation at the storage level and also on the management level. And this is then going into WP4. Of course, all these WP are connecting, and there are, of course, some feeder loops between them. And this is going to WP4 that it regards the integration of the system, and also, of course, on the construction that will be then transferred towards the WP5 that is on the validation and the demonstration that, of course, is also, let's say, starting earlier, since it also concerns the commissioning and the site preparation. This is, of course, it's quite important for a high TRL project where we are developing and deploying large-scale systems. Okay, next slide. Thank you. Yes, in the project, we have 3 demo sites that will be run for 12 months. One in an island in the Azores, Garciolica, one in an industrial site in Portugal, in Maia. The first one is coordinated by Garciolica, the second one by Cavat, and the third demonstrator instead is in Fraunhofer city in Pünzell in Germany. Main use case will be islanded grid, an industrial microgrid where we can use the storage for peak shaving, but also for self-consumption. The provision also of grid services, and of course the support to EV charging. Now, next slide, please. Going to a bit more details. So regarding demo 1, this will be in Sonai campus in Maia, Portugal. Cavat is the demo owner and demo leader. It's an industrial and business park, and here we have renewable production with solar PV. We have already present another lithium-ion battery. There are EV chargers and a cogeneration plant. Here we will install the aqueous hybrid energy storage system that will be developed and built in SMHYLES, composed by the Reidus for battery in a 50 kilowatt system, 8 hour, and an aqua supercapacitor, 100 kilowatt, 20 seconds. Second demo site instead. Next slide, please. This will be in Graciosa Island in the Azores in Portugal. It is an island, say, in the middle of the ocean. It's an off-grid island. Garciolica is the main energy provider for the island, and the hybrid power plant is composed already by 4.5 megawatt wind farm, solar 1 megawatt solar PV, an LTO battery of 2.6 megawatt hour, and a 4.6 megawatt digital power plant. We will integrate in this hybrid power system also our salt-based hybrid energy storage with a molten salt battery of 750 kilowatt hour and the supercapacitor of 250 kilowatt 10 seconds that will be used both for increasing the RES penetration and so reducing the curtailment, but also for providing services to the local grid in the end, to the local DSO. Next slide. Yes, last but not least, the demonstration at the Fraunhofer ICT Research Campus, where we have already in place a microgrid, also integrating an hybrid energy storage system. We have already in place a vanadium flow battery and with size of 1.4 megawatt hour and a 900 kilowatt supercapacitor. Here, the plan is to retrofit the current hybrid system by expanding the capacity of the batteries. And this demo site is owned and, let's say, by Fraunhofer Institute of Chemical Technologies. So the current status, we're well advanced with the design phase. So on WP2, it's more than 70% completed. The VPT is half, let's say, of advancement. We are, let's say, during the development phase of the innovation. And of course, we already started WP4 and just started in this month the WP5, mostly concerning the cell preparation. We have already 3 public deliverables that will be released this year as soon as we have them officially approved. So please do stay in touch. Let's say next slide, please. And you can check on our website as soon as they will be officially released, and stay tuned on our LinkedIn page. Here there's also my contact. Thank you very much for your attention.
Perfect. Thank you, Eduardo, for this introduction to the very interesting SMHYLES project. Quick comment, please recheck again if you have your microphones muted. If not, please do so now. Everybody except our next speaker, Olivier Delea. He is working for the project HIHELIOS, and he is research director at CEA in France. Olivier has 20 years of expertise in project management, surface engineering, additive manufacturing, and colloidal lithography. He holds a PhD in optoelectronics, and now I'm not sure if I pronounce this right, HDR, maybe, in engineering science. This seems to be some kind of a French title. And he's leading multidisciplinary teams and managing high-impact R&D projects. And for his collaborations with the industry, he has gained more than 50 patents. So I'm looking forward for your presentation, Olivier, on the project HIHELIOS.
Thank you very much, Daniel, for this introduction. Good morning, everyone. So I want to present the HIHELIOS project. So can you go to the next slide, please? Thank you. HIHELIOS project is part of the Horizon Europe called Horizon, focused on hybrid electric energy storage solutions for grid support and charging infrastructure under the BAT4U EU partnership. Launched on December 1, 2024, it spans 42 months with a 6 million euro budget. The consortium includes 12 partners from 6 countries: France, Belgium, Norway, Greece, Slovenia, and Ethiopia. Key players include battery manufacturers, Watt Forever and Revolta from Belgium, Energy Pool from France for grid flexibility, ROE from Greece for energy software, plus use case owners Daphne, InnoX, and Vito, and RTOs and universities like the coordinator CEA, as well as Flanders Make, Vito, Sintef, University of Ljubljana, and RIMA in University. Next slide, please.
Laura, can you do full screen, please?
Sorry?
This is a full screen, but since this is a PDF, I cannot do more than that.
Okay, I'm sorry. Okay. Please, Olivier, continue. I'm sorry.
The HIHELIOS project aims to maximize renewable energy penetration through innovative storage solutions. Our goal is to deliver a TRL7 modular hybrid energy storage system, or HESS, combining high-power LFP batteries or supercapacitor with high-energy second life NMC batteries. Using off-the-shelf components and repurposed EV battery modules, We will custom design HESS for 4 real-life use cases, from supporting fast EV charging in Norway to energy sharing and EV charging in Belgium, and to renewables integration in Tylos, Iceland, in Greece, through aggregating production and storage and supporting weak end of the grid. Supported by digital models, this approach addresses practical energy storage challenges. It's a step towards sustainable grid support. Next slide, please. About the technological concept of HIHELIOS, our HESS system will be able to be connected to microgrid operators, aggregators, and utilities thanks to its cloud abilities. It links to renewable production as photovoltaic systems and EV charging infrastructure via a multi-layered control system. This includes an energy management system for overall planning optimization regarding economical but also environmental targets, a power management system for efficient power distribution between the different assets, including both batteries, and a battery management system for monitoring and control and safely operation of batteries. The setups support grid services and EV charging by balancing high energy and high power needs. Visualized here, the architecture ensures modularity and flexibility. This design leverages existing technologies while pushing innovation for stationary application, aligning with sustainability goals. Next slide, please. The HIHELIOS approach progresses through technology readiness levels. We start at tier 5, building on prior work like scalable HESS architecture from the EU's CBAT project, originally developed for marine use at TRL 5-6, and move to TRL 6 with system integration and lab testing. By the project's end, we aim for TRL 7 with real-world demonstrations across the 4 use cases in 3 EU countries, helping for market and replicability studies. Post-project, the demonstrators are aimed to stay used, and our roadmap targets TRL 9 for full commercial deployment within 3 years. This phased strategy ensures robust development from concept to validated prototypes, then to market-ready solutions. It's a structured path to deliver sustainable hybrid storage, enhancing grid reliability and renewable integration supported by Horizon Europe funding. Next slide, please. The work is split into 3 steps across 8 packages. Step 1, technology development, covers work package 1 to work package 4, accurately defining use cases requirements, digital tools for modeling and sizing HESS, building the HESS architecture and controls. Step 2, demonstration, is work package 5, where we test for 4 HESS units in real use cases. Step 3, exploitation, spans work package 6 and work package 7, assessing impacts and scaling up via business models. Work package 8 ties it all together with project management. This structure ensures that we innovate, validate, and market a game-changing hybrid storage platform. Next slide, please. To recap, HIHELIOS pursues 6 key objectives. First, we develop a modular, scalable HESS architecture for stationary use with first and second life batteries. Second, we create a digital simulation framework for optimal design across grid applications. Third, we built a robust cyber-secure control system. Fourth, we optimize models for real-time and state-of-health diagnosis. Fifth, we engineer and demonstrate HESS at TRL 7 across 4 sites. Sixth, we conduct socio-techno-economic and life cycle assessment for business cases and exploitation. These goals drive our mission to enhance renewable energy storage supported by Horizon Europe. Thank you.
Thank you, Olivier. for the introduction to the project HIHELIOS. And now I want to, let me check the chat very quick. No, there is no specific question to this presentation. Now I want to head over to our panel discussion. And for this, I want to introduce a couple of more people to our virtual table, so to speak. And I want to start with Linda Barelli. She is working for the EU project Stories, and she is associate professor at the University of Perugia. She has a Master of Science in Mechanical Engineering and a PhD in Industrial Engineering. And she is Deputy Coordinator of the Sub-Program 2 within the ERA Joint Program on Energy Storage. She's in a scientific way responsible for the energy storage and hydrogen laboratory at the University of Perugia, and she performs research on energy storage, renewable power generation, and the integration in power systems, including hybrid energy storage systems, fuel cells, electrolyzers, and battery technologies. Linda, welcome to the virtual stage.
Good morning to everybody.
Great. Next up, I want to introduce you to Andrei Gubina. I remember I met Andrei at the Bridge meeting last year, the Bridge General Assembly, because he is also co-chair of the business models working group there. But his main profession is currently he's associate professor at the Faculty of Electrical Engineering at the University of Ljubljana. He, in his past, was a Fulbright visiting researcher at MIT, had an experience time in the industry, and since March 2007, he was head of the Laboratory for Energy Policy at the Faculty of Electrical Engineering in Ljubljana. He is a guest lecturer at the University College of Dublin. He has coordinated an FP6 project, is currently coordinating a Horizon 2020 project, and he is dealing with fields like power systems economics and deregulation, production planning under open electricity market conditions, risk management, and asset management in electric power systems, load forecasting, demand-side management, and so on. So, Andrei, welcome to the stage. I will continue. So we have two more guests to invite to the stage. I will continue with Peter Fischer, and I know Peter already from the European project HiFlow, and now from the project SMHYLES. But now, since September, he has a new position. He is general manager in the Green Transformation Department at Sumitomo Electric Industries Automotive Europe. He studied physical chemistry in Düsseldorf, worked on fuel cell research together with the German Aerospace Center for Fuel Cell Research. And since 2011, he worked at the Fraunhofer ICT, also currently still a partner, Fraunhofer ICT currently still a partner in the project SMHYLES, and gained their major experience in applied electrochemistry and large-scale redox flow batteries.
Yeah, hello.
Hello, welcome.
Hello, everybody.
And last but not least, Yves-Marie Bourien. He is the coordinator of HIHELIOS. He is a research engineer in stationary energy storage, stationary storage technologies at the Solar Technologies Department at CEA in France. And he has more than 15 years experience on stationary energy storage, mainly focusing on batteries for providing ancillary services, flexibilities, and for easing renewable energy networks integration at different grid scales. and he's also since 15 years at CAR. And there he works on several topics: performance and security and testing and characterization of battery technologies, sizing and modeling of battery electric systems, and self-consumption, grid flexibilities, and second life applications. Yves-Marie, welcome to the stage.
Thank you.
So the way we want to do this is I will ask a question. We wrote down questions beforehand, so we can already think about it a little bit. And we have to answer them in a very short period of time, because obviously we don't want to stretch the webinar too long. So I want to ask you to be precise with your answers, and let's see how the discussion goes on. I want to start with a question to Andre. And the question is, in a very general and broad way, what do you see the role of energy storage systems in the overall energy transition today?
Yes, thank you, Daniel. This is an excellent question, because storage and green transition doesn't only mean that we store electricity when it's available and discharge when it's not. It's actually storage is a new player in energy systems as of Clean Energy Package in 2018. And it's a key enabler in the 4 dimensions of the green transition, with decarbonization, decentralization, deregulation, and democratization of electricity supply. And this means, as decarbonization, shifting CO2 emissions, so reducing CO2 emissions by shifting to renewables in transport and heating and rest electrification. It can store excess green electricity coming from renewables and reduces curtailment of this green energy. In decentralization, we shift from central big plants to distributed energy resources like rooftop PV and community wind. And here, the storage helps with balancing of these variable renewables. In deregulation, then which means opening the energy markets to competition.
I'm also hearing this.
Yes.
Sorry.
Okay. And including the consumers and prosumers. And the role here is to shift power from centralized utilities to market-based players, which brings us to democratization, which means empowering consumers that can benefit from and to also influence the energy system. So storage empowers households to become active participants in this, and helps small users to become energy citizens, not just passive bill payers. So this is why it has a huge impact.
Okay, yeah, great. Thank you for this insight. So you would say this way of deregulation is very central to the whole process, right?
Yeah, central to the whole process, and that's why we're so lucky and happy to have them included in our power systems.
Yes, absolutely. I'm sorry, I think I hear Natalia, and I'm not sure if she hears us, but you have your microphone not muted, and we can hear background noise. The next question goes to Linda. Yes, so the question was, now we talked about energy storage systems in general. Now we want to go specifically into hybrid energy storage. And then the question would be, what are the trade-offs when integrating everything into one single device? So we have not then looking at different systems that support us, but maybe have this integration step. So what would you say to this question?
Okay. The first question is why hybrid? Why hybridization is useful?
Yes.
The answer is that hybridization allows to merge characteristics of different energy storage technologies, extending their application range and enhancing their performance in terms of both round-trip efficiency and extended duration of components subjected to degradation phenomena, as for example, for batteries, for closed batteries, or for electrolyzers, fuel cells. So performance of hybrid energy storage systems overcome performances of single technologies. And in general, it produces an increase in initial investment cost, but it produces lower replacement cost for degraded components and also lower operational cost. These aspects generally make hybrid system in 20 years or 30 years scenarios more convenient than the installation of single energy technologies. Other point is that in these scenarios, in this framework, optimization of hybrid architecture design, including power electronics, and optimization of the power management system becomes crucial. And with these aspects, I would like to open a further discussion with the experts within this panel.
Okay, perfect. Thank you. You finished. Okay, great. Well, thank you. So you would say there is a cost aspect, there is an efficiency aspect, and you would have a more optimal use. Would you also say that you are able to use maybe, I don't know, lower components that don't have to use as much power input, or that don't have to such a high stress on their performance, because when you use the hybrid systems, and you can, I don't know, use
you can optimize
power
the
levels.
operational. You can optimize the operational modes of each energy storage technology, so improving its performance and its duration. And at the same time, you can extend the operation range of the overall hybrid energy storage system. So you can address multiple time frame storage, so short-term, mid-term, long-term energy storage, depending on the energy storage technologies that you hybridized in your hybrid system.
Yes.
Okay, so for this reason, optimization, both at the design level and the management level, become crucial. And I don't go more in details, because maybe we can, with further questions and answers, we can address more in details these aspects. But my answer is to highlight some topics that become crucial in the case of hybrid systems.
Yes. Okay, then I want to head over, and Peter is already in the in the starting block. Directly to this.
I can directly connect to Linda. Of course, I can somehow blow in the same horn, because I completely agree with Linda's word that extending the operational range is super important. But also we have to look a little bit more in detail often, because often the cost benefit, or let's say the enlarged lifetime or less operational cost, it has to be proven that they outweigh in all applications. But what we see is that there crystallize out some major application where HESS could have a severe benefit, and we see it also in the projects. We see, for example, battery-supported charging. There is definitely a benefit if we combine long-duration energy storage with power storage. I see it in island application where load management can be very difficult. So there, if you can also provide frequency service, as well as maybe even if you have a very fast power electronic, like we see in HEHELIOS Project, that we can also make other grid services which are currently not usually paid, like momentary reserve. There's a third aspect I see in hybrid energy storage, which hasn't been addressed by most of the project, which is UPS application on all time scales. So this is also, I think, an important field for HESS, where some long duration systems like flow batteries or electrolyzers maybe need some assisting powers to directly cut in and fill the short-term gap. So in a combination, you can build, for example, UPS systems which run on all time scales, not only half an hour with like most of the UPS systems, but maybe even days, or even if you support them with mini grids, then for critical infrastructure, you can also extend it to several days or weeks. And this is, I think, an interesting thing when it comes to resilience as also an important part.
Perfect. So before I hand over to Andre, so this brings us already in the middle of the next question. This is what are the promising uses or use cases for hybrid energy storage systems, and specifically then what technology combinations are fitting for those systems. But Andre, you had a comment also to this.
Sorry, please, let's go ahead. I will edit in here.
Okay, perfect.
Actually, it's like this. The key point in what my colleagues have mentioned here is that the value stacking, and here the hybrid energy storage can help with it because it adds multiple sources of revenue by providing various services at the same time. And here it's important to keep in mind that when we scale the storage, the revenue, the sources don't scale linearly with it. And here the hybrid can help with the scaling problem. This is important part.
Right. I mean, if you think about, for example, also, I think the same issue is for the charging stations, right? For electromobility. If you build it for one car, it's okay. If you have to build a whole station on the highway, it's a whole different level of planning and products that you need. Yes, Linda, please. You're also here. I wrote you down with grid application. So.
Okay, I think that's energy storage and hybrid energy storage implementation for grid support services is crucial within the clean energy transition to guarantee stability and safety of power grids. And again, some use cases refer to power smoothing coupled to renewable plants, load leveling, frequency regulation, voltage regulation, and so on. So we have several multiple use cases, and which generally include as an energy storage service both the short-term and mid-term energy storage time frame. So, as I said before, hybridization is useful mainly coupling power-intensive technology with more energy-intensive technology, and specifically short-term technology that are useful to provide short-term energy storage with mid-term energy storage. So specifically speaking in terms of specific technologies, supercap or flywheels that can be coupled, hybridized with batteries, and this can provide some benefits specifically in case of a closed battery, since we can allow the batteries to work over a more smoothed power profile. And it is useful to reduce the stress over the batteries and to enhance their duration. So we made some assessment about the benefit, the obtainable benefit, and obviously the benefit is strictly connected to the specific applications. But if the design is optimized and the power management strategy is optimized, also very significant gain in battery lifetime enhancement can be obtained. For example, for a frequency regulation application in a microgrid, we investigated a flywheel coupled to a lithium-ion battery, and according to our design and our PMS, we obtain after 3 years of equivalent operation a reduction of 10 percentage points in terms of the capacity fading of the battery. So the capacity fading of the battery is reduced in case the battery is implemented in a hybrid energy storage system in a significant extent.
So, and this study you just mentioned, is this part of the STORIES project?
Yeah, it's part of the study. Specifically, it was made by the experimental activity is made at KIT in Germany. And I assessed to the KIT infrastructure thanks to a transnational access call funded thanks to the STORIES project.
Okay.
So we had the chance to test our hybrid energy storage system with a model of the battery and the physical flywheels in the scale of hundreds of kilowatts.
Okay, well, that's perfect. I think in one of the next webinars, we will also have an introduction for the whole STORIES project, right?
Yeah, thanks.
Perfect. Okay, Christopher, I wrote you down for the transportation aspect of usage of hybrid energy systems, and what combinations would you think work best for those?
Thank you very much, Daniel. So in the push towards zero emission vehicles, hybridization or hybrid energy storage systems could pave the way for balanced performance across driving scenarios when we're considering electric vehicles. And I was hearing, I just heard Linda talk about using even super caps. Like Haven is focused on having two different battery technologies where we use LFP for high energy and LTO for the high power. So in this case, I would say that having a battery technology for electric vehicles would reduce complexities of the architecture, because if you in some EV cars that include supercaps have like a linear voltage discharge profile. So this would need more DC converters and controllers for stabilizing the output voltage. However, if you have like a good high power battery in this electric vehicle, you would have a more optimized space usage, and of course we're talking reduced cost, because this is a reduction in complexity in the architecture of the electric vehicle. So yes, I see hybrid energy storage systems providing more balanced performance and extended range for electric vehicles for those of us who have range anxiety. So yeah.
And there is no aspect of weight. I mean, hybrid system sounds more heavy than single system.
That's correct. That's correct.
Okay.
At least this is where our project, the project like Haven, paves the way for research into batteries that have a high power density, and how it's optimized to have more power per weight volume per weight ratio in these EVs. So yes, but for now I think the state of the art is super capped. So I'm positive that Haven can, or projects like Haven can, pave the way for research into high power batteries being utilized in electric vehicles.
Okay, well, no, that's great. Peter, do you remember the Spanish company C2C? They made a solution for trucks, right, with super caps.
Yes.
But this was for starting, or I don't remember 100% what the application was. Or Christopher, do you know them? C2C?
Yeah. For starters, usually, yeah. For starters.
Yeah, okay.
This is when you have motors, usually you have a starter, and then you need usually more power than regular.
Right. Right. Okay. Well, maybe that would be also a great connection, Christopher. They were part of the HIHELIOS project, and are they also on SMHYLES? I don't have this.
Yes, they are.
They are in SMHYLES. So maybe it's a nice connection because they have this connection to trucks and they produce supercaps. So
no, I see.
Okay, heading over to Peter. Energy services. So again, the question was, but you already said a couple of words about this. So what would be the most promising technologies also and the most promising use cases? What would you say about that? And also, what would you say about the projects that the pilot projects that where you have seen what is working and what is not working, right? Because that would be a really great combination.
Yeah. So I think there are several, of course, services in the grid. Especially interesting is definitely the islands where load management is more difficult. So as an island energy service provider, you need to have a different load management than if you have really a wide distribution grid. So this is definitely more demanding, and for this, of course, you need somehow reserves, and you need to react fast. And also, if you don't have any spinning generators, also you cannot shift power in the very short duration. So what you're missing or lacking is momentary reserve. And there it's really interesting when you're working with renewable power plants, so like with solar or wind, it's very nice if you can work with very fast inverters. There are now developments of super fast inverters, and this, of course, need additional to your energy storage. You need a high power component to react fast or to push energy fast in or out of the grid. And therefore, hybrid energy storage could be a very nice alternative to support islands, especially when they have less conventional power plants or very little power plants in the grid. This is, I think, very important. I also highlighted before that for critical infrastructure, we will maybe see in the future more protection by either by somehow UPS solution or or resilient mini grids, which could be separated from regular grids, but by DC intermittent circuits where storage and renewables can be connected, because DC grids can be stabilized very nicely, and then you don't have a switch anymore like in a typical UPS solution, but can continuously feed into this DC intermittent circuit. And like actually today, very small UPS solution are built. You can today build it bigger because all the components are there on the market and in multi-megawatt range. So an important thing what we see is that we need, of course, more DC component. We need switch breakers. We need protection of the DC grid. There we see newer components hitting the market and also making this cheaper. This is driven by automotive industry, and I hope we can see there more DC components which help us to build these very advanced solutions. And what we haven't mentioned also is combining or building a bridge to the heat sector. So a lot of parts can also be interested to connect it to heat. We made a project where we used, for example, flow batteries as a heat storage in a building, but also it could be thought bigger. The heat sector is the least defossilized sector currently, and there also, for example, in combination with fuel cells, where waste heat is generated, we can add also another component by intersectorial connection. I think this is also an important point.
Yeah, absolutely. I mean, this is also on top of the list in the whole European discussion, right? The exchange between different energy systems and yeah. So, but all these things you were able to have a look at the Fraunhofer ICT, right? They have a really huge demonstration capability there with a wind turbine and a grid and everything.
We've built this 2 megawatt demonstrator of virtual inertia together with a supercap and a large-scale redox flow battery on one connected DC intermittent circuit. We also, this was part of HIHELIOS Project, and we also built other demonstrators like B-Flow with KLT, where we use a flow battery as a heat storage in a student dormitory, which we equip with a lot of with battery storage, a hybrid between lithium-ion battery, redox flow battery, and the heat storage unit. And yeah, these were very interesting projects where we could already demonstrate at a very early stage the benefits of hybrid energy storage. Yeah.
Perfect. Thank you. So now we have 10 past 11. In this third question that we have, I still have Andre here. So I would like to ask you for your part, and then we have to see how we want to continue given the time frame. But Andre, still we are in the area of uses for hybrid energy storage systems and what technology combinations might be best. And I have written you down with energy services together with Peter. So
yeah,
maybe you want to share some insight.
Yeah, thank you, Daniel. So in Haven, we're currently looking into provision of various energy services at the same time. So looking at the automatic frequency response regulation up and down, looking at we're looking to combine it with EV charging, with manual frequency response, frequency response regulation, and also including the PV generation. And this here we're looking at the operation strategy that's key here to optimize the high power and high energy parts of the batteries, and especially from the economical point of view, like what we mentioned earlier, the economics is key here, because it's very nice to play with the technology and with the cool technical problems. But on the other hand, we need to look at where are the revenues coming from, how we're going to pay for this. And this is where the markets and the connection, so not only the power system where the HESS is connected to, but also the markets playing. And they are in various states of deregulation all over Europe. There are important advances where these ancillary service markets like Mari, Picasso, other systems are put in place all over Europe, and this is where we're going to connect to it. Thank you.
So this financial aspect, that is something that you do in the project, so that is part of your research, right?
Yeah.
Okay, perfect.
Please go ahead.
No, I totally agree. I mean, it's very important to have, on the one hand, to know what is technical possible, right? So what can we achieve with the systems? But then in the end, if nobody's buying or implementing it, well, was all for nothing. So it should be a very feasible solution for everyone. The next part of questions would be about challenges and barriers with Eduardo and Yves-Marie. Now, we have, well, 12 past 11. Eduardo, Yves-Marie, what do you say? Will we have a specific webinar on challenges and barriers together with the other projects? Or do we want to have a short discussion right now?
Yeah, it could be a topic of a specific webinar, I would say. The discussion is quite large for today and very interesting on the use of the system. So maybe having these challenges and barriers more widely discussed in a specific webinar could be interesting idea.
I agree totally.
Okay, perfect. So, Yves-Marie, would you have anything specific to add for the use and specific systems? Would you have a comment or?
No, it was really already complete, but I totally agree with the stacking of the services and it is directly linked to the challenges for the software side of hybrid energy storage system to be able to change the services and to address different kind of services, power or energy services, depending on the operator and during all the life of the project and the system, because services can change during the life. But we can see that in next webinar, I would say.
Okay.
Thanks.
Perfect. Then thank you all for joining. Thank you for your contributions. I think it was quite an interesting start for a series of webinars. I also think that the next webinars will be more specific, let's say, on the technical aspect and on the scientific aspect of special topics. Please have a look at our websites. There will be announced the new webinars. We will also use the bridge. For this webinar, we asked the Bridge initiative to send around a reminder for our webinar to specific projects related to hybrid energy storage, and they did this. I really like this, so we will also use this channel, but we will use the homepages, and there is no central mailing list, but let's say, however you heard about this current event, you will hear about this in the same channel. You can follow me on LinkedIn. I will also post this on LinkedIn when there is an event, or follow the projects on LinkedIn, SMHYLES and Haven and HIHELIOS, and we will announce also there the upcoming events. Good. I think that's it. I don't see any more questions from the audience. There was a lively discussion in addition to the talks that we had in the chat, but no specific questions. Then thank you everybody for your contributions. Thank you for joining in, and see you next time. Bye.
Thank you very much.
Have a good day.
Bye-bye.
Thank you. Bye-bye.
Bye.
Bye-bye.